Hey, hello. Let's start the class. In this class, we will discuss the continuity equation that integrate the generation and recombination of excess carriers and their spatial and temporal distribution. The continuity equations serve as fundamental relationships describing the movement of carriers in semiconductors, considering throughput and diffusion currents, as well as the time-dependent variations and space distributions of carriers due to their generation and recombination process. This equation is important for understanding the electrical characteristics of semiconductors. Before the main class, let's review the concepts we learned in the previous class through an example. We have a p-type. We have a p-type silicon semiconductor doping with boron. Excess electrons and holes are generated by exposing light, right? The generation rate in this example is 10 to the 20th power per second cubic centimeter. The recombination lifetime given as 1 microsecond. For simplicity, assuming a steady state condition with no variation in carrier concentration over time and setting Ni to 10 to the 10th power. Then let's determine the thermal equilibrium concentrations and excess carrier concentrations. Additionally, we will calculate the total carrier concentrations and their product NP. First, P0, which represents the thermal equilibrium concentration of holes. This concentration is determined by the doping level, right? It will be determined by the doping level. And since boron is doped to the extent of 10 to the 15th power, the hole concentration is also the same. The minority carrier concentration, which is the electron, can be determined using the mass action law. So applying this mass action law yields a result of 10 to the 5th power, right? And next, for the excess carrier concentration, we just assume the steady state condition. So the generation rate and recombination rates are equal to 10 to the 20th power. Since the recombination rate can be defined using the recombination lifetime and the excess carrier concentration. So the excess core concentration can be calculated using a recombination lifetime as follows. Continuing, As the current situation involves continuous exposure to light, electrons and holes are always generated in pairs. Therefore, delta n should be considered equal to delta p. And next, the total hole concentration will be obtained by adding the excess holes to the original thermal equilibrium concentration. So in comparison to P0, we can observe that there is not significant difference. So we call this situation is referred to as low-level injection. The concentration of minority carriers, electrons in this case, also can be obtained by adding the equilibrium concentration to the excess electron concentration. Comparing it to holes, there is a substantial difference. The total electron concentration can be considered almost equal to the excess electron concentration. So in a low-level injection, for majority carriers like holes, there is almost no change compared to the equilibrium concentration. While the equilibrium concentration is maintained, the concentration of minority carriers, electrons, experience a significant increase due to the excess carriers. This situation where there is a rapid change in the minority carrier concentration and almost no change in the majority carrier concentration is referred to as low-level injection. And finally, let's multiply the concentration of electrons and holes. While the scale of Ni is 10 to the 20th power, and we can observe a significant difference. That is, in a non-equilibrium state with excess carrier generation, we can confirm through calculations that the NP product is no longer equal to Ni squared, right? So we can find out. And let's see the next examples. The following example is related to quasi-Fermi level. At this time, let's consider N-type silicon semiconductor doped with donors at the concentration of 10 to the 17th power. Additionally, let's assume that the excess carriers of 10 to the 15th power are generated in this example. First, the total the total electron concentration is given by N0 plus delta N, where N0 is the concentration of donors. Therefore, the electron concentration can be expressed as follows. Then the minority carrier core concentration is similarly given by P0 plus delta P. And using the mass action law to find P0 at this time, only for P0 for mass action law, and adding delta P, we obtain a value close to the excess carrier concentration. So this situation also indicates a low level injection. Therefore, when multiplying the electron and hole concentration, we get a value significantly different from Ni squared. Now, let's find the quasi-Fermi level in this scenario. Next, when we calculate the quasi-Fermi energy level, we can utilize the previously derived equation with slight modifications. Therefore, we will use the quasi-Fermi level instead of the Fermi level, right? Since we already know the KT and C, we can determine EC minus EFN. In other words, the gap between the EC level and the quasi-Fermi level for electrons, EFN, on the energy band diagram is 0.15 electron volts. When applying the same method to calculate the quasi-Fermi level for holes, we find that it is 0.24 electron volt. Consequently, when drawing the energy band diagram for a semiconductor in a non-equilibrium state, both Fermi levels, EFN for electrons, EFP for holes, will appear simultaneously. Alternatively, understanding it differently, observing an energy band diagram with two separate Fermi levels indicates that each corresponds to the quasi-Fermi levels. Each corresponds to the quasi-Fermi level for electron and for holes. So these help us comprehend that the semiconductor is in a non-equilibrium state. During our discussions so far, our goal has been to interpret physically and formulate equations to calculate the current when a voltage is applied to a semiconductor. To achieve this, we have learned various concepts. To calculate the current flowing within a semiconductor, it is necessary to compute how the carrier concentration change over time. Based on what we have learned, factors that contribute to change in carrier concentration over time include the application of an electric field leading to throughput and the occurrence of diffusion when a concentration gradient is present. Additionally, carrier concentration can change due to the phenomena of excess carrier generation and recombination. Therefore, by formulating equations that describe throughput, diffusion, and the generation and recombination of excess carriers together, we can interpret the distribution and motion of carriers. So this equation is collectively known as continuity equation, and we will now derive this equation. But before that, let's examine what flux is. So in a situation where particles are flowing, flux is defined as the number of particles passing through a unit area in a unit time. So it represents how many particles pass through a unit area in a unit time. A flux can be easily calculated if we know the current density. We have already learned that the current density can be obtained by multiplying charge, carrier concentration, and carrier throughput velocity. We find that when multiplied accepting the charge term, it represents sorry it represents the number of particles passing through a unit area in a unit time, right? Therefore, if we have information about current density, such like in this way, just dividing it by charge, just dividing by charge, give us the flux. So we can find out flux such like in this way. Okay, then let's start to derive the continuity equation. So to derive the continuity equation, let's consider a small volume with dimensions dx, dy, and dz. First, we will focus on the number of holes increasing per unit time within the unit volume dx, dy, dz. So let's imagine a flux of holes that are flowing in the x direction, leading to an increase or decrease in the number of particles within this unit volume. Assume that the flux of a horse only exists in the x direction and there is no flux in the y or z directions. So let's fpx represent the whole flux at the x location. Consequently, the number of holes flowing into the unit volume dx, dy, dz per time is given by fx dy dz, considering the whole flux multiplied by the cross-sectional area. This one, cross-sectional area dy dz at the x location, only for this x location. Next, consider the generation of horse within the unit volume due to thermal energy. So the number of horse generated per unit time due to thermal energy within the unit volume is given by the generation rates multiplied by the volume. So Gp dx dy dz. And now let's examine the number of holes decreasing per unit time within the unit volume. So if there is an inflow at the x location, there will also be an outflow at x plus dx. So these fx plus dx represent the whole flux at x plus dx location, number of holes flowing out of the unit volume per unit time is given by fx plus dx dy dz, considering the whole flux multiplied by the cross-sectional area here. So here, so dy dz and fx plus dx location. And additionally, considering the recombination of holes, the number of holes disappearing per unit time within the unit volume due to recombination is expressed as the recombination rate, which is the current hole concentration divided by lifetime and times the unit volume dx dy dt. In summary, the net increase in the number of holes per unit time within the unit volume can be expressed as the product of the rate of change of the whole concentration per unit time and the volume. So this can be expressed using the Taylor expansion and further simplified, leading to the continuity equation for force. And the similar approach can be applied to derive the one-dimensional continuity continuity equations for electrons. Here, the flux can be obtained by dividing the current density by their charge, right? However, the total carrier concentration, which is the sum of the thermal equilibrium states and excess carriers, becomes a function of time and position, right? So it is a function of time and position. Therefore, attempting to substitute this expression into the continuity equation. So when using this one, using here and here, when using these expressions and solving out the continuity equation becomes complex and difficult by hand, right? So to simplify, let's just assume uniformly doped semiconductor. So originally, the concentration of P0 and N0 could vary with position due to varying doping levels. However, assuming a uniformly doped semiconductor would treat them as constant. Ultimately, we can express the equations as follow here. Although these equations appear complex, a detailed examination reveals that the original expressions for total carriers transform into expressions for excess carriers, right? So this transformation arises from treating P0 and N0 as a constant. So when you see the first term, it involves the diffusion constant, so indicating its relation to diffusion. The next term involves electric field, so indicating its relation to throughputs. And finally, the last term includes contributions from generation and recombination. In summary, if we can solve these continuity equations, we can obtain information about carrier concentrations and subsequently calculate the current. Then let's conclude this class with a brief explanation of ambipolar transport. What happens if excess carriers and holes are generated at a specific point in a semiconductor and an electric field is applied? Electrons and holes having opposite charge would naturally move in opposite directions, right? However, the spatial separation of excess electron and holes will creates an internal electric field, generating an internal force that attracts them toward each other, preventing their apartment. So it will preventing this apartment because of this internal electric field. For instance, in an n-type semiconductor, if excess electron and hole pulses are generated, the external electric field initially causes them to separate. However, at some point, this induced internal field brings them back together and move as a pair. So move as a pair. This means that electrons and holes always move together, propagating as electron hole pairs. Therefore, the movement of these paired excess carriers is termed ambipolar transport. The prefix MB implies on both sides or both, indicating that carriers of both polarities move together. So electron and hole pairs move with single mobility and the single diffusion constant. The question arises: which characteristic, either holes or electrons, will dictate the movement of these pairs? The ambipolar transport equation, explored in the next class, will help us understand whether the movement follows the characteristics of holes or electrons. In conclusion, in the ambipolar equation, the ambipolar diffusion coefficient, ambipolar mobility, and recombination parameters, or signify the diffusion coefficient, mobility, and carrier lifetime of excess minority carriers. This means that even a slight separation between excess electrons and holes, leading to a minor concentration gradient, can induce a significant internal electric field, allowing both particles to diffuse and drift together. Therefore, with excess electrons and excess holes nearly neutralizing each other, we can interpret their collective movement as undergoing drift or diffusion with a single effective mobility and effective diffusion constant. The fact that these parameters are associated with the diffusion coefficient, mobility, and carrier lifetime of minority carriers is crucial. The condition of charge neutrality implies that the concentration of excess minority carriers equals that of excess majority carriers. Consequently, excess majority carriers undergo diffusion and drift together with excess minority carriers, and importantly, the movement of excess majority carriers is determined by the parameters of excess minority carriers during this phenomenon. This ambipolar behavior is a fundamental concept in understanding semiconductor properties. Okay, that's it for today's class, and thank you for the listening.